So everyone, a very warm welcome to our Support Vectors weekly meetup. The topic today is small language models are the future of agentic AI. This paper is fairly recent. It came about a month ago, and it's provocative because it goes contrary to what people have been saying, or for example, what the neural scaling laws are saying. So let me bring forward the two principal counter arguments to the use of small language models. By small, let us start with a preliminary definition. Anything that you're running on your machine, roughly speaking, is a small language model. And that's a definition these authors also pick. So, for example, if you're going to OpenAI 4.0 or something like that, then that's certainly not small, or Anthropic is certainly not small. But if it is local, quite likely it is local on your machine. It's quite likely small, or fits the definition of small. So within the large language, the whole AI community, and specifically researchers amongst the LLM, there has been a general belief or a well-established result, which is called the neural scaling laws. The neural scaling laws roughly say the following. If you want to build a really powerful general purpose, a generalist model that's capable of many, many diverse things, that's versatile, what you need to do is bring a lot, just make the model bigger. As you scale up the model, it acquires a lot of capabilities if you can successfully train it or train it properly. Now, what is the definition of training a model properly? It is to bring lots of data, because if you don't bring enough data, then the model will just overfit to the data. Right? So we know that that's the classic overfitting problem. And the second thing you need to do is train on that data long enough, sufficiently long, so that if for no other reason, then you can have at least the grokking moment, pass the grokking moment, so that the model learns to generalize and abandons memorization. This was a topic, by the way, in our previous 2 weeks ago, we did another paper reading, which it sort of relates to, which is that how much do language models memorize? And what we realize is that a language model memorizes approximately 3.6 bits per parameter. So what you need to do is you need to bring so much data and train it for so long that you pretty much convince the model that it cannot memorize all of it, and it has to go into the grokking phase, and it has to go into the generalization phase. It learns from that. So broadly speaking, that is the neural scaling law, that for a given parameter size, this is the data set size, this is the amount of compute you need to bring to properly train it. And then, of course, there's a paper from Google, the Chinchilla Optimal, which gives you the aspect rate. What are the proper combinations to the cocktail that you need to bring to grow up this baby? Now, one of the observations over the years has been that, people believe that there is no point in taking a model, the current model, or a small model, and fine-tuning it for purposes, a domain, let's say finance or something like that. And because the bigger generalist model that will come down the pipe in a few months will make your fine-tuning sort of irrelevant, your domain adaptation sort of irrelevant. And there has been studies, and I'm just reminded of one particular study, which was, I believe, done by Bloomberg, who tried to train a finance model in the days when it was GPT 3.5. And they spent a lot of effort training it for the finance domain, or fine-tuning it for the finance domain. And then came GPT 4.0, and what they realized when they did a bake-off, they realized that actually a 4.0, even as a generalist, was outperforming in finance over the fine-tuned Bloomberg model. And that was a warning, I suppose, to all of us that at the end of the day, the neural scaling laws rule. And if you want to have better models, better performance, just go with bigger models. Right?
I'm wondering, so when you say fine-tune, however, they were then fine-tuning like ChatGPT. When I think
No. They took their own model and went about doing it.
I
But
see,
they
and then
put the same footprint, the same process.
this fine tuning we mean by modifying the weights, right?
That is right, by modifying the weights. Yeah. So they trained their own model with lots of data, and then they did some further fine tuning. The usual thing, the supervised fine tuning and all of that. They built a custom model only for finance. And to their great surprise, it did very well. It did better than GPT 3.5. But then when GPT 4.0 came up, which was a much, much bigger brain, then they realized that the generalist 4.0 outdid the domain specific model that Bloomberg had spent quite some time training. And so that was quite a interesting case study. And from then onwards, I believe people have always felt that just wait for the bigger model to come, right? And bigger models solve some problems, right? Now, there is also a belief in something called the semantic hub. That belief says, in a sense, that as you scale up the model, and this model, therefore, to train it, it has to be exposed to more knowledge. It is informed with a lot more knowledge and trained with a lot more knowledge. It begins to understand the gist of many domains, or generalize across domains. So what happens is, or so the belief is, that even for specific tasks, it is able to do much better simply because it brings the wisdom of a much broader perspective to it. Right? So that's the purported belief of a semantic hub. Now, semantic hub perspective is not so empirically grounded. There are no clear evidence that it is so, but it is a common belief that people have. The fact that neural scaling laws are there are, of course, very well established. So with these two backdrops, um, now when you put it and then you see a title like this, small language models are the future of agentic AI, you wonder, what are we talking about? And shouldn't we all just be building models, our agents, over this big, centrally hosted for GPT 4.0s and so on and so forth? Shouldn't we just be making API calls to them because they are the smartest things around? Right? And that is the thing that this paper is going to question. Now, I must also say that the reason we selected this paper here at Support Vectors is because we have been coming actually for the last more than 6-7 months to a very similar conclusion. Now, when we came to the conclusion, what we found is, and I'll just park that fact for you guys here, what we found is that because agentic systems or agentic AI essentially uses task decomposition. The very first thing you do is you plan a complex task into subtasks. And when you do that and you break it up into many, many subtasks, quite a few of the tasks are just pure tool calling. Right? Now, to just call a tool, you really don't need a PhD. Right? For example, to hit something with a hammer, a nail with a hammer, you just need the ability to know that hammer is the tool that you need to use. Right? So a tool calling it reaches saturation point very early on. Models like tool formers are fairly small models, and they can be trained. And you don't get anything more by going to very big models. The other thing that we observe is that many of the tasks are very simple tasks, like rephrasing or putting some facts in 200 words or something like that, or writing it out as a data structure in JSON, or many similar tasks that we do. And do we really need to bring in, for example, a model whose brain size is 1 trillion parameters, or is 7 billion or 13 billion parameter model just about enough? And what we came to the conclusion is, we actually sit and start with a big model, and then successively for each task, we keep decreasing the size of the model. We keep going step by step down to see at what point a smaller model doesn't work for us. Right? And we find that quite often our sweet spot has been between, anyway, for very simple tasks, sometimes it is just 2 billion parameter models, but generally it is between 7 billion and 30 billion parameters. Right? And for some other tasks, we do use 70 billion parameters, but broadly speaking, between 7 and 30 is the bulk of our utilization. But there are 10% cases, there will be some things, like, for example, getting the planning right and so on and so forth, where we find that using the frontier models, the really big brain helps a lot. There are certain open domain questions where you really benefit from having a big brain. So our general consensus here has been that use a heterogeneous combination of models. So another way to put it in common sense term is use the right tool for the job for each task, right? And the tool for every task need not be the biggest brain. Or another way to put it that we do colorfully is that if you want to plant a rose bush in your backyard, you don't have to requisition a caterpillar, right, to drive over to your place and an earth digger to do the job. Right? So, so with that as a context, so you can imagine that my views are colored in favor of what the argument this paper is making. And this paper is an argument piece. It doesn't have a lot of empirical graphs, etc., etc. It does have some empirical facts, but broadly, it is not a breakthrough, but a position paper. So with that, let us go and see what it argues. And what are the core arguments, actually? And I believe we can go through this pretty quickly. The abstract of this paper says large language models are often praised for exhibiting near human performance on a wide range of tasks and valued for their ability to hold a general conversation. The rise of agentic AI systems is, however, ushering in a mass of applications in which language models perform a small number of specialized tasks repetitively and with little variation. So, this, by the way, the crux of their argument rests upon this statement. And frankly, this statement is broadly true, though not always true. Like we found that there are a small class of tasks which do require a lot of reasoning, even in agentic systems. And bringing in big brain does help. But anyway, we'll move forward. Here we lay out the position that small language models are sufficiently, and this word is crucial, are sufficiently powerful, inherently more suitable, and necessarily more economical for many invocations in agentic systems, and therefore the future of agentic AI. I would like to dwell a little bit about this, but I'll start with the third point. See, when you build agents, and one of the things you do is you realize that your agents are making um, a, a plethora of calls to the LLM. Some calls are simple, some are complex, etc. But nonetheless, you are inundating the LLM with lots of queries. And when you do that, the latency matters. If you're calling a frontier model and it takes a few seconds for it to get back to you, all of those seconds add up pretty quickly. Right? The other thing is, obviously, it's not economical from the perspective from you're paying for the tokens, right? And but even at the producer side, at the side of the frontier models, the open AIs of the world, think about it this way: they are hosting these massive models in ginormous data centers, consuming insane amount of power, amongst other things. Imagine that what is the ecological footprint of serving a query. At the end of it, it gets amortized over lots of queries. But wouldn't you rather have that those big models were serving requests that really needed big brains, rather than, can you please convert this this table into JSON, right? Which can be the nature of many of the queries. So now they go on to, so that's the one point. The other thing they say is small language models are sufficiently powerful, as we'll see, this is broadly true, inherently more suitable. The inherently more suitable part, they will argue, comes from the fact that if you have, amongst, for many reasons, but amongst the reasons that you can fine tune local models, you can run them on small hardware, you can run many instances of it, and you can get very, very high inference speed, very low latency, and high performance from that. Right? Those are the benefits of using small models. So anyway, they continue on to say, our argumentation is grounded in the current level of capabilities exhibited by SLMs, the common architecture of agentic systems, and the economy of LM deployment. We further argue that in situations where general purpose conversational abilities are essential, heterogeneous agentic systems, i.e. agents invoking multiple different models, are the natural choice. I couldn't agree with this more, because that is what we believe here. We believe very much here at SupportVectors that that is the right approach to do. use the right tool for the right for each task that you do when you do task decomposition in an agentic system. So I will just park it is that strongly agree for me, and I would like to hear if anybody has a contrary view.
But
We
Ashish,
discussed the potential barriers. Yeah, please go
sorry,
ahead.
one comment here, right? See, this particular statement is true regardless of LLM or SLM. Technically, in agentic system, I think it makes most sense to use different models for different tasks. Like a
You're
reasoning
speaking from
versus a non-reasoning model, as an example.
Oh, that's right. That's right. Pradeep, yeah, we discussed this in previously. Very much so. You're very much right. Even if you use only big models, then also you will have some choice. Reasoning versus non-reasoning, vision language model versus just language model. Those choices still remain. Very, very true. Right. But I suppose what the author here Pradeep refers to is that even if you're within a very narrow domain of language tasks, nevertheless, you still need heterogeneous agentic systems. Which heterogeneity comes from one of the points that you made. It may be a reasoning task, it may be a simple task. Right? So they will talk about it more. But great point. Then they talk about, we discuss the potential barriers for the adoption of SLM in agentic systems and outline a general LLM to SLM agent conversion algorithm. So, well, their general LLM to SLM, like how do you migrate from LLMs to SLMs in an agentic system? They call it the LLM to SLM agent conversion algorithm. Frankly, like, that algorithm is nothing but mostly common sense, one by one replace and see whether it works. So, but I think the value of this paper is to provoke a discussion. So we'll go there. Yeah. Our position, formulated as a value statement, highlights the significance of the operational and economic impact. Even a partial shift from LLMs to SLMs is to have on the AI agent industry. We aim to simulate discussion on the, and this is what they are trying to do. And I'm hoping, actually, I would really like to know what all of you guys think. Myself, we aim to stimulate the discussion on the effective use of AI resources and hope to advance the efforts to lower the cost of AI of the present day. So, and they have a location here you can put in your comments. Now, they start out with some pretty strong facts, and I'll just mention it, industry trends. The deployment of agentic AI is on a meteoric rise. Recent surveys show that more than half of large IT enterprises are actively using AI agents, with 21% having adopted just within the last year. Right? So that's a pretty obviously high growth. Aside from the users, markets also see substantial economic value in AI agents. As of late 2024, the agentic AI sector has seen more than US 2 billion in startup funding, was valued at 5 billion, 5.2 billion, and was expected to grow to nearly 200 billion by 2034. So what the expectation is in 10 years, it will 10x, it will go 100x, right? So that's a massive growth rate that we are doing. So put plainly, there is a growing expectation that AI agents will play a substantial role in the modern economy. The core components powering most modern AI agents are very large language models. So they emphasize the point that when they mean large, they mean very large. It is the LLMs that provide the foundational intelligence that enables agents to make strategic decisions about when and how to use available tools, control the flow of operations needed to complete tasks, and if necessary, to break down complex tasks into manageable subtasks to perform, reasoning for action planning, and problem solving. As a little aside, if I may, I just want to remind you that the classic definition of an agent is autonomous piece autonomous piece of intelligence. In other words, it has some agency, agency or capacity for independent decision making. That's an agent. Agent and agent exists in a contextual to an environment. And the agent observes the environment this is the classic definition, for example, in any AI textbook, for example, Narvik, Peter Narvik, and so forth. And excuse me, and it responds with actions, or it sort of actual actions that it does, and you observe through sensors, and you do your actions through actuators or effectors or actuators, as you may call it, using this. So this is your fundamental cycle. Agents act, and people often say observe, reason, act. This is your cycle for the agent. So laying out the basic definitions upfront. So obviously, these days, most of the agent, the intelligence part of the agent is essentially the LLM. So that is the statement that they make here. It is the LLMs that provide the foundational intelligence that enables agents to make strategic decisions about when and how to use tools, control the flow of operations needed to complete a task, and if necessary to break, etc., etc. Right? So just giving a perspective on that.
Asif, just
Yes.
one question. So, does it basically come to the fact that now the performance matters more on the designing of the agentic system, and that with small language models would just be better than large language models? So, the importance now comes on the planning of the agentic systems rather than the choice of models?
See, Atisha, the way I would say that broadly, yes, it is true. Because see, the point of diminishing returns comes in. If your job is to convert, let us say, some text or some table, let's say that you have a simple table and you want to make it into a JSON. Quite a lot of it is not about the LLM. The task is too simple. Right? There are situations where the LLM matters, but as you build agentic system, our experience is that much of the, for example, if you take the workshop on AI agents here, you learn that much of the hard work of creating really effective agentic systems that do keep succeeding at their goals is the rigor with which you think about it more as a systems design problem rather than just use big brains. The careful orchestration, the fine tuning of the model, the very proper construction of the tools that they can engage with, and setting up the goals and the context for the prompting, all of those ultimately become far more important. And then you take the model that works and you experiment and you take the model. Quite often you know what it will be. You take the model, and the point, I suppose, the gist of what they're trying to say is don't go blindly using LLMs over an API. Don't use a frontier model. Amongst other things, it is high latency, it is high cost, and there are better ways of doing it. That's the main point there.
Okay.
So a typical AI agent. So this is the word that they're pointing out. A typical AI agent then simply communicates with the chosen LLM API or OpenAI or Anthropic or whatever endpoint by making requests to centralized cloud infrastructure. That is a fancy word for saying one of these big guys that host these models. LLM API endpoints are specifically designed to serve a large volume of diverse requests using one general. So we all know this. I won't go into that. I'll just jump over a few statements. Now, one interesting thing that they mentioned is that this operational model is deeply ingrained in the industry. It's this way of thinking in the industry that it forms the foundation of substantial capital bets. While the market for LLM API serving that underlies agentic applications was estimated at 5.6 billion in 2024, the investment into the hosting cloud infrastructure surged to 57 billion, 10x that in the same year. The tenfold discrepancy between investment and market size has been accepted because it is assumed that this operational model will remain the cornerstone of the industry without any substantial alterations, and that large initial investments will deliver returns compatible with traditional software and internet solutions within 3 to 4 years. So that is the main thing. We have all got sort of tunnel vision into that this is the only way to do it. What they are saying, there's a different way. Right? So I will jump a little bit over it. They make two basic definitions. First is they very smartly they define in a sort of timeless way what is a definition of a small language model. They didn't give a number. They didn't say, okay, a small language model is a 2 billion parameter or 10 billion, 5 billion parameter, 10 billion or 13 billion or whatever, because that definition will become obsolete tomorrow as hardware gets better. So they said SLM is a LM that can fit onto a common consumer electronic device. I suppose that's a fancy word for workstations or laptops, and perform inference with latency sufficiently low to be practical when serving the agentic request of one user. So in other words, it should work on small laptops. At the same time, it shouldn't be so big model that you have to wait for one token at a time, slowly to come out every few seconds. Right? It has to be practical. That's it. And a large language model is anything that is not a small language model. So it's the converse of it. Anything that doesn't quite fit onto your laptop basically is a large language model. And they go into a lot of reasoning on why this makes sense. And then they make three crucial claims, which are the claims that we will elaborate on in this paper. The first claim is, principally, the small language models are sufficiently powerful to handle language modeling errands of agentic applications. So this is it, agentic applications, because they have a lot of task decomposition, breaking up the task into smaller subtasks. They're saying that small language models are principally sufficient, most of the time sufficient. The next statement is more interesting. They say inherently more operationally suitable for use in agentic systems. And the third is necessarily more economical for the vast majority of LLM use than their general purpose counterparts. So powerful, operationally suitable, and more economical. That's sufficiently powerful. And they elaborate on this position in a very interesting way. I'll go over it one by one. What they say is we support views 1 to weeks, all the three assertions, by the following non-exclusive arguments. So they say, first is the assertion, SLMs are sufficiently powerful to take on the task. So they point out that over the last few years, the capabilities of small language models have advanced significantly, and they have been getting better and better. And I suppose I will skip the wordings, but I'll just give you the main idea. So Microsoft Phi series, if you would recall, they mentioned that the Phi 2.7 billion parameter model achieves common sense reasoning scores and code generation scores on par with 30 billion parameter models while running 15x faster. Phi 3 small at 7 billion achieves language understanding and common sense reasoning on par with code generation scores running up to 70 billion models of the same generation. So what is this Microsoft Phi? This was actually quite a remarkable series of models. The first one came out with a provocative research paper, a very nicely titled research paper, I would say, not provocatively. It said, what was the name of the paper? It was Textbooks is All You Need.
Asif, something to note here is that this is comparing a Mamba attention, though, which is a different.
First one. Yeah, we'll come to Mamba. We'll come to that in a moment.
Okay, because
I'm still on the Microsoft Phi series.
Okay, because I thought that this was suggesting when it's comparing it, it was using Mamba, but it sounds like that's not the case.
No, it's not necessarily suggesting Mamba. What it is saying is that if you remember, the Microsoft Phi series started with a research paper, textbook is all you need. What was the main message of that? people were training big models with noisy data. So Microsoft said, okay, what happens if you train a model with absolutely clean data? And what is the benchmark of clean data? Nothing like a textbook where every sentence has been reviewed by reviewers. Right? So they say that if you take very, very clean data, then you can train a smaller model, and it will like basically give much bigger models a run for it. Right? It will have comparable performances and much bigger model, and that was very, very eye-opening at one time. So in their argument, they are saying that for many, many tasks, like common sense reasoning tasks, if that is what you need, why not use, for example, a 5-3 small? That is one possibility. The second one, Alyssa, is the one that you mentioned. NVIDIA's Nemotron Edge family is genuinely not a pure transformer model, and it's a Mamba transformer model. Now, what's a Mamba transformer model? For those people who don't know, I'll just talk a little bit about it. And this, by the way, refers to the point you're making. Mamba transformer, Mamba relates to a kind of architecture that are called state space models. State space models. Right? Mamba was the first one that came out, and after that, they have been going through continuous evolution. Now, what happened is when Mamba came out and the state space models came out, and they have gone through evolution, SSS, and all of that, then people observe that they actually solve a fundamental problem. Transformers, or the attention, has a quadratic compute problem. Remember, the transformer has this problem of KQ. This in the attention is softmax V. The inner product of K dot Q, right? Attention is defined as this. And this is the troublesome part. This is the troublesome part because this is quadratic compute. And that is what has been a core problem that people have been trying to ameliorate when they deal with attention. But Mamba came out and they needed a linear compute, a different architecture, state space model. The problem with Mamba that people observed, and I think a lot of it is still under research on why and what is happening, is that they don't seem to remember things as well as transformers do. So people then started creating hybrid architectures like Mamba transformer, like this Nemotron Edge family is a Mamba and transformer hybridized together so that you have the best of both the worlds. And when you do that, the benefits are somewhat in between. You don't get the enormous speed up of the linear compute that pure Mamba gives, because you're mixing in a transformer with its quadratic compute, but at the same time, it's way faster than a pure transformer architecture, right? And so people have been doing that, and recently it has been giving people a lot of very good results. So this is what they mentioned, that NVIDIA's Nemotron Edge family. Then Hugging Face Small LM. Oh, by the way, just today, I think, or yesterday, I noticed that the next version of Hugging Face Small LM, I believe 3 has come out or something like that. But again, it speaks to the fact that a whole slew of new models are coming that are rethinking the neural architecture itself. And I want to make a point here. As you look through this list, and then NVIDIA's HIMBA, then NVIDIA is a HIMBA model, and they mention NVIDIA quite a lot, but there are other people also doing pure Mamba attention-based models, which also gives you many things. Then DeepSeek R1 Distill series. So when the DeepSeek R1 came out, it shocked the world because it was open or source, visible in daylight, that you can do pure reinforcement learning and induce reasoning in models. But what was more practical and effective was that you could take the reasoning capabilities of R1, that ginormous model, and distill it down to much smaller models. So, for example, you could take Quen, not only smaller versions of DeepSeek models, but they went to all their competitors. For example, they went to Quen, which is a competitor to, I suppose, DeepSeek, and they went to Llama, another open source competitor, Mistral, and they managed to distill the reasoning capabilities of R1 down to smaller models. So what it meant is all of a sudden these small models now had reasoning capabilities, which was, and this is a pure distillation approach that they took. And then and look at the variety. Please remark at the whole variety of approaches that these different models are taking. A DeepSeek Retro 7.5B, a little bit older, but what they took is, which has been there for a while now, it took a RAG-like approach. It basically say, how about we bundle in a model along with some knowledge, some external text database. Essentially, what I would say is a model and the whole RAG rolled up into a model. Right? That was the DeepMind's Retro 7.5B. And once again, observe how differently they have architected it. And then there is the Salesforce XLAM, which is very specific to tool calling, fine-tuned. It's a model that is specifically fine-tuned for a tool calling, which is a core agentic activity. Because if you notice, the agents engage with the world, they observe. The sensors and effectors are basically tools, right? Agents engage with the world through tools. And so you have models like XLAM specifically meant for tool calling and doing an exceptionally good job. In fact, it surpasses even the state-of-the-art generalist models like GPT-4o and Cloud 3.5 of those days. Right? So now, as I read through this, the first thing that occurred to me, and the paper goes on to talk about it, is that observe that it is not just scaling up a vanilla LLM, right? See, when we talk of the neural scaling laws, what the neural scaling laws very clearly say is that if you take a model and you take a scaled up big brother of that model, the scaled up big brother of the model will be a much better generalist than this model. It will do even specialized tasks better than the smaller guy, right? And sometimes if you just fine tune the smaller guy, the big brother will still beat it in many ways, right? That was the main message of the scaling laws and the belief of this semantic hub and all of that. But observe something very interesting. These people are not just blindly scaling it up. In each case, they are doing something different. The 5 series is bringing clean data, much cleaner data than you normally train an LLM with. And Nematron Edge is hybridizing Mamba and Transformer, right? And likewise, each one of them, say Himba is going Mamba and attention in a slightly different way. DeepSeek is doing distillation. DeepMind is essentially bundling up a RAG thing into a model. And Salesforce is focusing on absolutely doing one task specialization, right? And so the question is, when you do this, is it still fair to claim that because of the neural scaling laws, you're better off with larger models? So they argue that it is not the case, that when you do all of these, you find that smaller models, they do much better, and they do performances both comparable to big models, or oftentimes they beat the big models, right? And you see it over and over again. You see these numbers 25 times, or 8 billion parameter XLAM is beating something like trillions of parameter size models. And DeepSeek R1 with its distillation, Quen outperforms much larger. Like, think about it this way. A Quen 7 billion parameter model distilled with R1 reasoning is outperforming Claude 3.5 or GPT-4o. Just think about the implications, how big the implication is, right? So what it says is that besides just increasing the size of the model, there are alternate paths that are just as effective, if not more effective, in getting high quality abilities in models. And that's the main message, I suppose. The second point that they make is SLMs are more economical in agentic environment. That goes without saying. If you have a small model, a small number of parameters, common sense says that the forward pass matrix computation will be a much smaller matrix computation. If you have a 7 billion parameter model versus a 700 billion parameter model, the size of the matrix multiplication itself as the forward signal propagation happens, signal transduction happens, would be far, far smaller, right? And so it's no surprise that they say serving a 7 billion SLM is 10 to 30 times cheaper than the 72. Well, of course, why would it not be? And then when you compare it to that, the compute cost of a big GPU, a big LLM, then it gets even more. The other important point that so inference efficiency you get much faster inferences. The second is a fine-tuning agility. See, if you have a small model in-house, you can actually fine-tune it. If you have a ginormous model, even in-house, it's harder to fine-tune because you need more than the same rules apply. Fine-tuning is essentially training. You need to bring more data. You need to train it for longer, right? Because there are more parameters. And so you get actually fine-tuning agility. You can keep on. And this point that they make is very, very true. If you go to websites like, for example, Sevit AI, you notice that all these kids are busy creating beautiful art. And in any one of the beautiful art, they would have created all these fine-tuned LoRa adapters. And any beautiful picture they create has half a dozen LoRa adapters plugged into it. And then they create such beautiful and evocative images that you wouldn't want to create such images using just a ginormous model. And I suppose those kids make this point much more compellingly and in a way, empirical way, than we could make just by looking at those pictures. The next point they make is edge deployment. Advances in, well, if it is a small enough model, you can actually do edge deployment. And now, increasingly, I don't know how practical it is so far because I have not done edge deployment of these models, as in on the cell phone or inside the browser or something like that. But there seems to be some early indication that one could go that route. If the model is sufficiently small, you could do inferences with them at the edge. Right? But obviously, I have no experience with that on that assertion, but it is there. Parameter utilization. The next point they make is the parameter utilization. This is very important. One of the observations that is there is that imagine that you have a huge model. Let's draw it out. Imagine that you have a huge model, and when you do a query, it leads to signal transduction. It turns out that very, very limited paths get activated. A very sparse subcircuit circuit gets activated, right? The rest of it were, for all practical purposes, you can say that to the first approximation, they don't participate in the signal transduction. So then the whole question is, but you have this big model running in memory. It's consuming power. It's consuming resources, right? And so there is an inefficient parameter utilization. All these parameters are just sitting there for that particular query. And so obviously, if you bring in another query, another path will get signaled. Now, the point that they're making is that there is evidence that when you use smaller models, they have a larger proportion of the parameters activated. Or in simpler terms, if you have a smaller brain, then answering a question is a whole brain activity, or much more of a whole brain activity than when you have a ginormous brain and you can that brain could pretty much sleep its way through to an answer, metaphorically speaking. So that is that. There is also a modular systems design. This point, I suppose, needs to be made. People often say that if you you're too fixated on models when you do agentic framework. We agree with that. Agentic frameworks are actually more systems, AI systems, and you need to approach it with a systems design, modular approach. And you see some of this emerging, like, for example, instead of having one team, just one ginormous team of agents, or one agent doing everything, the first level of modularization is you bring in many agents, each doing different things, being responsible for different areas. And then the next level of modularization is that, I suppose, you have little crews or little agentic teams achieving, or departments achieving something, and then exchanging results with each other. So there is a lot of progress. For example, if you look at frameworks like Crew AI, they do have the notion of crews achieving entire subtasks, and then between them there is a flow framework, the flow API that helps communicate the results through them. Right? So the above mentioned Lego-like composition of agentic intelligence, scaling out by adding small, specialized instead of experts, instead of scaling up monolithic models. So they make a big deal of it. Actually, we find that it's really true. As we complexify our agentic system, we often find, especially for enterprise use cases, that what you're doing is a large laundry list of fairly simple things, enterprise workloads. None of it is like, for example, uh, I mean, a few of them require deep thought, but broadly, most of them are simple tasks, right? If so much signal is there, could we take this and see if there are exceptions happening? Is there hardware failure happening, or something like that? Many of these tasks that you do in the enterprise are simple enough that you can do with small pieces of intelligence, but there are just lots and lots of them, right? And enterprise applications are big, ginormous bundles of or portmanteau of these little pieces out there. And so we do resonate with this thing that a Lego-like approach helps. Their next assertion is SLMs possess greater operational flexibility in comparison to LLMs. And again, if you have small language models, many things you can train them, you can adapt, fine tune them, you can deploy them. What we find is that this is our experience. When you deploy it on VLLM, let's say, or especially when you use distributed inference frameworks like Ray inference on a cluster, VLLM and Ray and all of these together, it really helps that on the limited hardware you have, you can maintain a heterogeneous collection of LLMs, each of them good at something that your agent. So basically, you specialize or make an agent very good at something by fine tuning that LLM or fine tuning that model. And then that small model, you put it into that pool, that inference server pool, and it becomes available on the hardware. So that is our observation. So they say that this efficiency enables rapid iteration and adaptation. And you can obviously go on adapting to requirements and so forth. The other point they make, which is a sort of non-technical but very useful, it's a social point they make, which is the democratization. So this is now a change of pace from technical discussions to a different point. They're saying one particularly notable and desirable consequence of SLMs, flexibility, when you put in place of LLMs, is the ensuing democratization of agents. When more individuals and organizations can participate in developing large language models with the aim of deploying in agentic systems, the aggregate population of agents is more likely to represent a more diverse range of perspectives and societal needs. What it means is if we are all fine-tuning our own models and making agents out of them, then from the different walks of life that we come, our models and our agents will truly reflect the color, the personality, the concerns of those domains or those walks of life or those societal concerns. And that is a good thing, they say. This diversity can then help with reducing the risk of systemic bias and encourage competition and innovation. The point being, if all of us are using just one model in the universe, then it's a very monocultural phenomenon. Whatever it is, whatever systemic biases are, there is no escaping that. Whereas if we are all taking our own small models and fine-tuning it, then we create a far more diversity, essentially, right? And they go on to say, with more actors entering the field to create refined models, the field will advance more rapidly, which is a fact. Research is best when all sorts of researchers jump in and they all have divergent perspective and divergent priorities. And small models open the door to that. I think they make a lot of assertions. Now I'll just go over them a little bit faster. Agents expose only very narrow LLM functionality. What they're saying is that, see, when you write agents, the agent is specialized. This one will use the LLM to parse the search results that the search tool brought, Supper, for example, brought from the web. right? Do you really need a general purpose LLM that can, amongst other things, solve deep math problems for just rewording or taking or harmonizing a bunch of search results into a good paragraph about it? You don't need it. One metaphor that sort of comes to mind is, see, these large language models, you can think of it as a very, very, very expensive high-end Swiss knife, right? It has everything. It has a screwdriver, a knife, a scissor, and so forth. But if all you need is to is a is a screwdriver, aren't you better off getting a high quality screwdriver, which will cost you a lot less than getting a very, very expensive large language model? I mean, a very expensive Swiss knife, whose screwdriver will be mediocre at best. Okay? That's the point. And they make this point in a very interesting way. They say what happens is that when you use that Swiss knife, they say this very interesting statement. From this perspective, the underlying large language models that was engineered to be a powerful generalist is through a set of tediously written prompts and meticulously orchestrated context management, restricted to operate within a small section of its otherwise large palette of skills. So what you're saying is, here's a large language model, which is a PhD in 1,000 fields. But one agent is using one tiny ability from that. And what you do is you try to invoke that little piece by doing all sorts of careful and tedious prompt engineering and context specification and guardrails and so on and so forth. Why not take a small model and specialize in it? I suppose one very clear proof of that is the Salesforce paper itself that we encountered above. If you remember the XLAM paper, if you encounter that, what they did is Salesforce took just a 8 billion parameter model, and it says we'll train you to do one thing and one thing only, tool calling, right? And they realized that it became the best tool caller that was there, the state-of-the-art tool caller at its time when the paper was published. And so why not take that approach is the main point they're making. The next thing they say is agentic interactions necessitate close behavioral alignment. So this is about back and forth. Quite often what happens is the results come, you do something, or further interactions. Like for example, if all you want is for it to become JSON, do you really need a general purpose model that knows how to write it in JSON, XML, LaTeX, HTML, so on and so forth? You probably don't. Right? It's sort of making the same point. Agentic systems are naturally heterogeneous. This point comes from the fact, I believe, that agentic systems are meant to solve complex problems. Complex problems inherently have different moving parts, like different tasks. And inherently, those tasks are different from each other. They're heterogeneous tasks. Otherwise, you could have bundled all of them into one go. And so they're saying agentic systems are naturally heterogeneous. The corollary of that is why not, for each task, find the right model rather than use one common model for all the tasks? That's what they're saying. And then finally, they're saying agentic interactions are a good source of data, which is basically common sense. See, if you're using local models, you can actually capture all the queries and the responses and observe their patterns and use them to fine tune the model later on. Suppose you notice that through observability platform, you find that certain kinds of queries could be done better. You would now start fine tuning the model a little bit more on that area. Right. So that's what they're saying. So alternate perspectives. Now they say, why do people disagree with them or could disagree? The first point is that the alternate views. This is the neural scaling law point, which is that let T be a single task. It's a bit of a formal language, but I'll say a single task using general language, and let L and S be large and small language models of the same generation, respectively. By same generation means using the same technical know-how. The only difference is in parameter size. The performance of L on T will always trump that of S. Very true. Generally, it's found to be true. And people have found that there's a non-negligible body of empirical evidence of the superiority of that. I mean, this is the neural scaling law. Let's not go over it. We all know that. The other is a more nebulous concept of so-called semantic harm, which doesn't really have as clear empirical grounding, but is believed that large language models have somehow understood the world better. So they give rebuttals. The rebuttals, they say that popular neural scaling laws studies have assumed the model architectures to be kept constant, which it is not. If you look at the cases, for example, these models, each of these models use a different neural architecture or a very different approach. They are not just smaller versions of the big models, big generalist models. They use, in other words, different approaches to make the model better, not just scaling it up. Scaling it up is just one approach, is the main point they're making. And the second point they make, I suppose, in their rebuttal is the flexibility of large language models comes to the rescue. Of course, small language models are flexible. They can be fine-tuned, right? And when you fine-tune, of course, now you're going orthogonal to the neural scaling laws. Reasoning is more affordable because you can distill reasoning into it, or you can induce reasoning into a model through reinforcement learning. You can actually do it on simpler hardware than on big hardware if you use smaller models. Right? So they go on actually arguing similar things. LLM inference will still be cheaper because of their centralization. This is the second argument people make, which is that, and this argument is actually, they acknowledge, is hard to refute. They're saying that, see, as a society, as a civilizational effort, suppose we all pool our resources and train a ginormous, mighty generalist model. Economies of scale will take over. And therefore, one could argue that the amortized cost for every use case will be lower than everybody having their own small models and going about fine-tuning it. And they acknowledge that that argument does hold, though at this moment the jury is out and the data is not clear that there are actual economies of scale saving. Right? From what I understood, that's what they're trying to say. Right? And then they talk about barriers to adoption. Why do people not adopt? Simply put, inertia. People are just conditioned into the belief that you should invoke big LLMs over APIs. Right? There's a lack of popular awareness. The other point they make is, very often small language models, they come short on benchmarks, but those benchmarks are comparing for general tasks. So generalist models do well. What we need is a new set of benchmarks only for agentic tasks. And there is a argument to be that, and this paper makes it, that if one focuses solely on benchmarks measuring the agentic utility of agents, the studied SLLMs easily outperform larger models. We already saw an evidence of that, for example, up here. In these examples that were given, amongst these examples, you could clearly see that not only smaller models achieve better results, results comparable to big models, sometimes they beat them, right? They outperform them also. So that is it. And I suppose that's the gist of this paper. Now they go on to say, how do you convert LLMs to SLMs? So there's a lot of, okay, remember to anonymize the data, privacy protection, and so on and so forth. And what you also should do is then cluster the data, cluster the user queries to see what are the use cases that are dominant, and then fine tune for that, and so on and so forth. Most of their so-called agent conversion algorithm, I suppose, would be called common sense. Now, these people say that it's a point of view, so they invite arguments, they invite a large discussion, and so would I. We are here all together, 27 of us. So perhaps I would like to hear what you think. I have been speaking for quite some time what I think. Yeah, please go ahead.
I'm assuming if you're building a crew of agents.
Would you mind turning on your microphone? There's a microphone, there's a button on it. Because then the remote people can hear you.
Okay, is that better?
Yeah.
I'm assuming if you're building a crew of agents, and each agent has access to an SLM, to orchestrate them, you would still need an LLM.
Yeah. So your question is that see, each agent, once it gets a task, it will invoke its underlying LLM, which may be sitting on an inference server like a VLLM or Ray inference, or whatever it is. You don't need that. But generally, for planning and task decomposition, general belief is, or at least what we do is, we use a LLM, always do, but we don't use the LLM throughout. What we say is, here is a task meant for a big brain. Here are the tasks that small brains can do, right? That's the approach we take. And not only that, many times a small brain, you can fine tune it for your purpose so that it really does much better than a generalist big brain, unfine tuned big brain.
So I guess in real world use cases, you'll always need an LLM SLM hybrid. It's not just one.
I wouldn't say always. There are situations where you can get away without it. Like, for example, people are now trying to train much smaller planning models, a smaller SLM, which is tuned for one thing and one thing only: planning, task decomposition, and planning. Right? Some people are creating SLMs which are really very good at deciding orchestration of interaction between agents. Right? So people are trying all sorts of effort. At this moment, the situation is frankly very fluid in this space.
I'm assuming SLMs will have higher risk of overfitting compared to LLMs.
The converse. SLMs, remember, a smaller brain, right? Less parameters. So overfitting is not the problem. Their main problem would be they may not be able to solve that complex task. Right? That's a bigger problem. Or they may not even have the context window, or they may not have. There are many other considerations that come in. You notice that, for example, if you take a very tiny model, let's say 7 billion parameter, then you can squeeze in only so much input. Bigger brains take these days they take near infinite size context windows. Right? So that is a factor that comes in. All right, guys. Any questions or any opinion? I would love to hear what you guys think.
Yeah, I have one question, Asi. Very great presentation. This was amazing, really. So perfect. Would you mind commenting also on the context window or context in general? Because I'm a big proponent of small language models, but I think the biggest issue is the context window is usually very small, right?
That is true, though that barrier in the last 2-3 months, that has been fast being shattered. I believe, for example, Quen 3 reasonable size. What is the size for Quen 3? 30 billion? Well, according to these people, they wouldn't call it a small, but I call it smallish. See, it depends on your definition. My definition of small is up to 30 billion, right? And I don't know what this is, what the 7 or 8 billion parameter models context window is, but for 30 billion, I believe it's 128,000 tokens, right? Which is an encyclopedia.
That's
So
pretty decent, yeah.
That's very decent. So this has been very, very recent, actually. In very recent months, the context window of smaller models has been really increasing, and they're able to handle it. I wouldn't say it's in millions, but it is pretty decent, and it gets the job done.
Yeah.
And sometimes, like like I take this example that you have to take search results and summarize it, right? Or just look for contradiction between the facts. You don't really need, like, for example, you don't need a big context window because they're just like top 10 search results that you're passing to it, right? Or you're looking for what is the general sentiment or whatever it is in the opinion about some product. So you found out all the product comments or feedback, and then you're looking for positive and negative sentiment and asking an LLM to do that. So small context windows are just, reasonable context windows are just fine. And also for something like that, frankly, any LLM is already an overkill.
Yeah, that's really interesting. I'm very curious to hear, Asif, like what you and or your colleagues' team experiences with the right type of orchestrator. So, I'm sure everyone here has heard of MCP. Like what has been the most performant along those lines? I'm just curious what people have seen.
And so this is a good question. Here is what we'll answer, because we are you heard the phrase herding wildcats. So our group is, everybody is experimenting with different things, but when it gets serious for something really not the research activity but building a product, then we have to give up our wildcats attitude, and then the game shifts. What we find is this: we are big fans of MCP for tooling, right? In fact, we go to the extent that suppose we have a RAG, even if it is an agentic RAG with graph RAG and everything thrown in, a well-done RAG on a domain. What we do is your typical expectation is that the RAC's interface would be a chat, right? OpenAI like chat, right? You would bring it in. But what we do that, of course. But actually, what we find is that we make special purpose RACs and we make them into MCP tools, right? Needless to say, just about every API that we consume, we have made into MCP tools. And if you look at APIs like Fast MCP, they have done an amazing job. Like in 3-4 lines of code, you can convert any public API into an MCP tool, right? And that's a blessing. So for tooling, MCP is the way to go. Now for agent-to-agent communication, that is the orchestration between the agent. And now the thing gets more interesting. We initially in our team at one time were big into AutoGen. Then we moved big into Crew. Then Crew wasn't exactly moving as fast as when the MCP came. So we got a little bit impatient, but I know that Crew AI now has all of that tooling. But in the meanwhile, we jumped into LangGraph, and we like LangGraph. So then now there's framework like Agno in our team, which we like quite a bit, and Pydantic AI that's coming. So in the open source community, these are the ones that we are heavy. But I would say that most of the heavy lifting we have done with Creo AI and with LangGraph. Now on the commercial side, we noticed that, for example, Google's recently the agent development kit. We actually like it, especially because of the debuggability, the very close inspection or under the hood's view that the Google's SDK gives to you. We really like it. The OpenAI's operator and framework, etc., is simple that you can consider. Anthropic's MCP, of course, leaves nothing more to be said. But there is something else that's happening. When you look at, so suppose you have your implementation in Creo and somebody has the implementation in Langer or whatever it is, two systems. There is a need for agent-to-agent communication across heterogeneous implementations. And people are now coming up with protocols for that. There are 3 protocols actually. Last week, Krishnan Ramasamy, he did an amazing presentation actually in the meetup, in which he showed the distinction between the 3 approaches. There is one approach which is the A2A, the Google's approach, which basically is a peer-to-peer communication. It says any agent can declare an agent reference card. This is who I am, and these are my skills. And another agent now has a protocol to communicate in a peer-to-peer way with it. That is the Google's A2A protocol. Then IBM has an agent communication protocol, which says there is a broker. Let's bring in a broker, very much like the old messaging system, enterprise messaging bus. Let's have a broker. And all the agents can communicate with all the agents in a hub and spokes manner, with the hub being the broker. Right? That is out there. And then, of course, then there is Cisco. And Cisco came up with a slightly different approach. It says that, hey, why all this? Why not get inspired by something like the DNS server? If you remember, all the DNS is a distributed ledger. It's a name. You just have a name server, and this name server copies from that name server, is in sync with other name servers. Any update in any name server propagates to the rest of the name servers in due course of time. So why not maintain a directory? Why not make every agent like a URL have a unique identity? And those identities are maintained by these distributed ledgers in some sense, like a domain name service kind of a thing. And therefore, agents can communicate by looking up each other through a DNS kind of a situation. And so they call it, Cisco calls it the Internet of Agents. So they all of these very nebulous, but very powerful ideas. If you think about it, each of these approaches makes a lot of sense. Now, which particular approach will prevail? Too early to tell, because these are all just, it's like freshly baked bread at this moment. Right? So we'll see.
Asif, I have one question, layman's question. So is distillation not better than SLM?
Distillation is a way to create really smart SLMs, right?
Okay.
Remember, what is distillation? Distillation is, so I'm a student. So I'm a small model, let's say, right? And I have a small brain. So I can learn by 2 ways. I can be given data, the same data. That data is there. And I can try to learn from this huge pile of data. But because I have small brain, See, if you think in terms of a universal approximator theorem, my approximation will be rough, right? It will be a gross approximation of the underlying ground truth. But now imagine that you bring a big brain, the teacher brain, right? Now that big brain looks at the same data and it comes up with a very nuanced and beautiful universal approximator, much nuanced and beautiful ground imitation or approximation of the ground truth. Much better way of making predictions and saying things. Now, distillation is simply saying that in my case, as a small brain, I can do two things. I can learn a little bit from the data, or better still, I can just learn to imitate the master, right? Or I can do both. I can learn, as I'm learning from the data, I keep a close eye on what my master is saying, what the big brain is saying, right? And learn to also imitate the master. So when you learn by imitating or the master, you're saying that the master, the teacher is distilling their much bigger and better, deeper understanding down to the student. That is me, right? Me as a small brain. So what happens is distillation was a discovery or the proposed by Sir Geoffrey Hinton, right, the godfather of this field, and it has been widely successful. Like if you are creating a small model, distillation is certainly one of your first go-to approaches you should take. Right? Take a bigger model and distill it into the smaller one. And then, of course, you can further fine-tune into whatever it is. Like, for example, you take Quen 8 billion or something like that, a small Quen model, and you can distill R1's reasoning ability into it. Right? And it works amazingly well. Right?
I'm curious about, in terms of if anyone's heard WIND, of Agentic, MCP, and all the other ones that you mentioned, like Fast MCP. Then there's these different players on the block. Have you, like Cisco with their own type of
Internet of Agents.
yeah, like their own spec for it effectively. If there's been chatter or wind of security in this realm.
Oh, big security. So agent to agent protocol, the good news is Google, IBM, and Cisco, all three being enterprise players, they give you, at least as a first implementation, already they support enterprise security, authorization and authentication is built in. Right? So OAuth, for example, is built in. And then once you have that, then the standard RBAC security, role-based authentication, kicks in. And all of those integration hooks are there. That's one nice thing actually with the A2A, the communication between agents. Each of the three approaches are security aware.
Yeah, that's very interesting. I wonder if there's any hackers that have broken that.
Well, let's just put it this way. Too few people even know that these protocols exist. It's just like I said, fresh off the oven.
Oh yeah, absolutely. I'm just curious if I mean, yes, OAuth is generally secure. But there's always a way, right?
There's always a way. See, the basic rule is that security is only a deterrent. It's never a foolproof. A determined hacker will always get in, some way or the other.
Thank you. I was just curious if anyone's heard. I know it's very all of this is a bit new, so it's good to hear what people are talking about along those lines.
See, a security expert who happened to be a participant here at SupportVectors once told me that the ultimate truth about security is that when you put a big camera on your door, right, and a big lock, visibly big lock there, all you're doing is you're deterring a thief. You're basically playing a zero-sum game because a thief comes, looks at this, all of this, and says, it's not worth the bother. Let's go to the neighbor's house. Right. And that is security.
I certainly feel that because I have a car that got broken into, and once they realized it was a stick shift, they quickly left.
Oh boy. Yeah.
Quick question.
I think somebody's saying something, but I can't hear it.
Just wanted to check if I'm audible.
Yes, now you are.
Oh, okay, great. Yeah, just want to quickly ask anything about the cost, like calculating the cost when it comes to LLM. Like, let's say I'm using some kind of cloud model with the tooling. I can see that using one specific model and using like various agents. I The input tokens and the output tokens can be calculated since it's a single model. We can determine that at the end. But if we are going with the SLMs, how do we like debug the tool chain and also like think about the calculating cost for each of these small language models if they are like inference of on different distributed systems or a single system?
No, that's a great question actually. See, when you call a frontier model, you pay API costs. It's very transparent. Right?
Mhm.
When you host it on your machine, then the question is, you're paid a capital cost. Right? You purchase the hardware, and on the
Mhm.
hardware, your teams are now launching the models. So you're not paying by the tokens. All you're looking at is the CPU utilization and the GPU utilization and asking, do I need to scale up the hardware? A bit harder to do, but I'll give you one data point that take it for whatever it is worth. See, guys, when you put a model, like our experience is that when we put the model in, we have always been a big believer in running models in our data center because half the time we are tuning them. Right. See, the thing is, you go on an endless journey on improving it, which you can't do if you use frontier model. Every time you think you got it right, you have another idea of making it better. And you keep doing all of that, funny games, and LoRa adapters and so forth. All that flexibility you have. But the main point, what we find is that we sleep much better because when our applications are in inference mode in production, we don't at all worry about raking up big bills. The cost is paid up front, up right in the beginning when we put the hardware. And if I have to guess, we pay, and I can say not just guess by just by looking at this is Silicon Valley, right? You knock on the neighbor's door, that's a startup, and they are paying API tokens. So let's just say that our total bill, AI bill, is much smaller. Our electricity bill is much bigger, but our total cost is much smaller.
Okay, I get what you're saying, like when it comes to budgeting, but let's say I'm running like a big model behind a proxy, and there are enterprise level users who have to connect, let's say, some thousands of users, like hundreds of thousands of users, and we'd like to set a budget for each of them for a day, let's suppose.
Oh, that is easy to do. That is easy to do. Actually, that is a strong argument in favor. So, see, all of these, that is just a decorator. So, when you do, let us see programmatic and system level thing. What you typically do is whenever queries come, you always associate a user context with it, and you always associate a token counter to it. The input token counter and the response token counter,
Count, yes.
and you always check against what is the quota of a user. So, that is more architecture and throttling at the level of the architecture. You would do that whether you run on-premise small models or you run, you make invocations to the on in-cloud frontier models, API calls to. You do that anyway, otherwise there'll be runaway cost in either case.
Yeah. Checking. Got it. I think, yeah, I got my answer. Yeah. Thank you. Thank you, Asif. Yeah. I also got an additional point on the budgeting. Yeah.
All right, folks, anything else? I look forward to seeing you next week then.
Great presentation. I just really wanted to catch that last one. I know it's recorded, but I hope no one else minds. Just to kind of go back to wrap up on that last point. So when looking at it end to end,
Yes.
that's when that is solved by, and then you mentioned the key, but I kind
Oh
of
yeah, cost the token. How do you sort of budget or ration the tokens?
no, that in terms of evaluation, sorry. Like when you're evaluating it end to end to see if it meets the goal.
Yes. Oh no, we didn't talk about that, but I can talk about that. See, in our case, right, we see agentic evaluation systems are in a very nascent stage in the open source, and generally they are evolving. What we do, I can tell you what you do. We do know what problem we are solving. So we are strong believers in a statement. See, a lot of people here in our team are physicists. And one of the great physicists, a thermodynamics person, Lord Kelvin, right, is famous for saying, you cannot improve what you don't measure, right? His full statement is more complicated. It says a subject has not risen to the level of science unless it deals with measurable quantities and so on and so forth. But what we do is before, right at the time we have a product spec, like what we are building, the first thing we do is we create benchmarks. We need some way to know that we are making progress. We do it right up front. We sit and think, what is the measure of our product? How do we measure it? And we go from there. We put an evaluation first approach.
Yeah, so that means what you're telling me is that you're putting an evaluation at each step for observability?
That is right. We do that a lot. Like for example, if you're looking at search, right? Then there are all of these measures like recall at K, precision at K, then MRR, then mean average precision, NDGC, and so forth. You you keep track of all of them, and observability platforms help you a lot with that.
Awesome. Thank you so much.
You're welcome. All right, folks, I look forward to seeing you. And folks, please do join our Discord link, and please suggest interesting papers for us to cover. Remember, we cover papers that obviously our meetup community suggests. So please do suggest some good papers. Recently, there has been a slew of great work coming, and we'll one by one cover those papers. Nowadays, we are doing 2 paper readings a week, Monday and Wednesday. Monday, we keep it practical and industry surveys, and as Wednesday, we keep it in paper reading. Look forward to seeing you folks next week.
Thank
Bye,
you.
guys.